Hello, my name is Robert Petrovic, and today I'm going to talk about my project to use machine learning to predict age in MRI scans. My goal was to develop a machine learning model that can accurately predict whether an MRI scan belongs to a young or old patient based on the image data. So accurately predicting a patient's age based on MRI scans has important implications for early disease detection, clinical trials and research studies, and understanding brain development and aging. For example, early diagnosis of Alzheimer's disease can lead to better patient outcomes by enabling earlier intervention and treatment. Similarly, identifying age-related changes in the brain can help us understand the mechanisms underlying neurodegenerative diseases. As you can see in this figure, there's a clear correlation between increasing age and increasing cases of Alzheimer's, Parkinson's, and ALS. By identifying early signs of these diseases through age prediction, we may be able to improve patient outcomes. In this project, I used the neurocognitive aging data release from OpenNeuro, which provided me with 52,976 MRI images to work with. First, I divided the data into train, validation, and test data sets. And then I pre-processed all three data sets by resizing and normalizing. And for the training data set specifically, I also went a step beyond and I augmented it with additional transformations like random flips and random changes to brightness and contrast. The rationale behind this was because working with MRI data presents some unique challenges compared to other types of data, including image resolution, noise, and variability across different scanners and protocols. So this way, the model was exposed to various transformations of the images, which helped it to become more robust to different variations in the input data. So with data augmentation done, I labeled the images according to the age group using the provided metadata. And then I created PyTorch data loaders to handle the input pipeline efficiently. For the model, I chose the pre-trained ResNet 50 architecture with transfer learning, which takes advantage of the CNN's ability to extract useful features from images without having to train the entire model from scratch. The choice of ResNet 50 for my project is justified by its deep architecture, residual connections, ability of the models to be trained on other tasks, and its proven performance and wide adoption. So by using a pre-trained ResNet model, I can take advantage of the features learned by the model on the large ImageNet data set in this case, and I can fine-tune the model on my specific task. This technique, as I mentioned, is a transfer learning, and it can significantly reduce the amount of time and resources needed to develop an effective deep learning model. So moving on from this, I defined the cross entropy loss function as the loss function to use, and I used the atom optimizer to minimize the loss function. The hyperparameters I used included a learning rate of 0.001, a batch size of 32, and 10 epochs for training. During the training process, I iterated over the training set using the data loader, and I fed the input data to the model. The model was validated on a validation set at regular intervals to ensure that it was not overfitting. The last fully connected layer of the model was updated to match the number of classes, which in this case was 2, young and old. And then it was fine-tuned during training, this last layer. This allowed the model to adapt its feature extraction capabilities to the specific task of age prediction while maintaining the pre-trained weights of the previous layers, which were established from image classification on the ImageNet dataset. I tracked the training loss and accuracy and saved the best model based on validation accuracy or loss. And I have a graph here just showing you how the accuracy was improving as I was training it. Just make sure I have, yes, okay. Yeah, so then I wanted to go into visualizing the hidden units. So to better understand how my model processes the MRI images and identifies features for making predictions, I visualized the hidden units within the model. By examining the feature maps from different layers of the truncated ResNet 50 model, I was able to get insights into the model's inner workings and the types of features it focuses on during the decision-making process. So in the earlier layers, I noticed that the model focused on more like simple patterns like edges and textures. And then as I progressed through later layers, the model was starting to combine those patterns into more complex features. Of course, this ultimately ends with it being able to distinguish young and old MRI scans effectively. So these visualizations not only help us understand the model's thought process, but it could also potentially give us a chance to identify room for improvement if there's any issues with the design. For these samples I have on the right, this was just from one specific model. but I just wanted to show you how the visualizations can get a little bit abstract, and it's just a very interesting way of demonstrating how the model learns to extract and combine features as it progresses through the layers. Obviously, there's a lot more hidden units I could have shown, but it would get very crowded on this slide, so I just picked a few to show. Right, so the model achieved a test accuracy of 90%, indicating that it can accurately predict age in MRI scans. I calculated the model's performance metrics using the area under the receiver operating characteristic curve, also known as the AUC. I also plotted the ROC curve to analyze the model's performance in more detail. So you can see I have an AUC score of 0.97. So it's clear that the model is excellent at distinguishing between young and old MRI scans. And I'm focusing on this metric rather than simply accuracy of the test set, because AUC score is less sensitive to class imbalance. I had about 7,000 images of old patients and about 11,000 images of young patients. So there's a bit of an imbalance there. So if the test data set has an uneven distribution of classes, the accuracy might be lower, but the AUC score can still be high if the model is good at ranking these instances, which proved to be the case. So in summary, my project successfully used machine learning to predict age in MRI scans, which has important implications for early disease detection, clinical trials and research studies, and understanding brain development and aging. The use of the pre-trained ResNet model with the test set demonstrated its ability to generalize well to unseen data. The visualization of the test set, the visualization of hidden units provided insights into the model's decision-making process and feature extraction. This project highlights the potential of applying machine learning techniques to the field of medical imaging and the benefits it can bring to patient outcomes in research. Thank you.